So we're going to do one of the last lessons in integral applications that will be assessed on your I-4 test. This is the area between two curves. Okay, so the key idea here is that we're doing the area between two curves. Now normally we've already covered the idea that I want to do an area under a curve. So let's say that's my function y equals f of x. And if this was x equals a and this was x equals b, and I was interested in finding this area under the curve, we already know based on I2 how to set up this area. We would go from a to b, f of x dx, and it's an area bounded by the x-axis, and then that would represent that green area under the curve. Now suppose I had two functions. Suppose I had y equals f of x, and I had y equals g of x. And let's say I was interested in the area under the curve for this function between x is equal to a and x is equal to b. So I'm going to represent this area in green. Now in order to find this area between f and g, we're going to take the area of just the upper function. So I'm going to find the area under the function g from a to b, which is this orange area, which goes right down to the x-axis. And that area is going to be larger, and I would want to subtract off the area under the curve of f of x, which is that smaller area. And when I do that, you can see that the area that will be left over is exactly the area that I want, which would represent the area between the two curves. So that's how we're going to do it. We're going to set up an integral. We're going to go from left to right. Where does the shading start? Where does the shading end? This will represent x equals a, x equals b. These are vertical lines. We're going to do our top function minus our bottom function. And we're going to integrate with respect to x. And that's what this theorem down here is telling us. That if we want the area between two curves, they're both continuous functions on that closed interval. We take the top function minus the bottom function from the left interval to the right interval. So let's go through and actually find an example. So I'm going to go through this example here. I'm going to do the graph up here. So they give me a function y equals x squared plus 2. I'm going to draw that in orange. So there's my function x squared plus 2. My vertex would be at 2 because the parabola has been moved up 2 units. I want to draw the graph of y equals negative x. So y equals negative x, which is given in the question. Let's highlight the parabola with that. They want us to do bounded by x equals 0, which is this vertical line. And they also want us to bound it by x equals 1, which is, let's say here, this bounded line. So we are interested in this yellow area under the curve between the two functions. So let's set it up. We want to ask ourselves, where does the shading start? The shading starts at the pink line, which is x equals 0, and the shading ends at the green line, which is x equals 1. We want to do the integral of the top curve, which would be x squared plus 2, minus the integral of the bottom curve, which is negative x, and we want to integrate with respect to x. Okay? So again, if you were to draw a vertical line on this yellow region, the orange function is on the top and the red function is on the bottom. And the orange function is on the top. So no matter where I take this slice, the orange function stays on the top and the red function stays on the bottom. So this is always my top. This is always my bottom. So let's go ahead and simplify this. So 0 to 1, x squared plus 2 plus x dx Now I'm ready to integrate. So add 1 to the exponent, divide by that number, plus 2x plus x squared over 2. And I want to evaluate that from 0 to 1. So I sub in the top value, sub in the bottom value, and then subtract. So 1 cubed over 3 plus 2 times 1 plus 1 squared over 2 is the top value, minus 0 is the bottom value. And then you just evaluate that, which is whatever that answer is. And you would work that out, and that would be the answer to represent that area under the curve. Okay. Now again, let's try a different example. So in example 1, my curves didn't intersect at all. But here, now we're going to get curves that are intersecting. Okay. So I'm going to pretend this graph wasn't given. I don't know what these graphs look like. So we want to make sure that you're able to solve the problem without the graphs being given to you. So they say find the area of the region bounded by the graphs of 2 minus x squared. So that's a parabola facing down, moved up 2 units. Okay, so that's my equation 2 minus x squared. This vertex is at 2. And the graph of x, which looks like that. So they're asking us to find the area of the region bounded by these two graphs. So let's highlight that region in yellow. You can see I've produced the exact same graph on the right. But again, these graphs would not be given to you. Now, you may want to ask yourself, what's important about these two graphs? Well, it is important to know where is the shading starting on the x-axis and where does the shading end on the x-axis. And those are represented by the intersection points between the two curves. So let's set those curves equal to one another and solve those intersecting points. So x squared, I'm going to move that to the right, plus x, I'm going to move the 2 to the right, minus 2 equals 0. Go ahead and factor that. X plus 2, x minus 1 equals 0. X is equal to negative 2 and positive 1. So that tells me that this intersecting point was negative 2. And this intersecting point was positive 1. This is like my A. Okay, so now we're going to set up our integral. The integral is going to go from the left point from where the shading starts to the right point. Now before I set up my integral, if I were to take always a vertical slice through that section in yellow, you want to ask yourself, is my top dot always on the orange function? And no matter where I put this vertical line, the top dot always sits on my top function, which is f of x, and the bottom part of the dot always sits on the red function, which is x. So now I'm going to do top function, 2 minus x squared, minus bottom function, and then I would just integrate with respect to x. So let's clean this up and integrate. So 2x minus x cubed over 3 minus x squared over 2. We would want to evaluate that from minus 2 to 1. Sub in the top limit. Take that expression minus, sub in the bottom limit, which is 2 times negative 2 minus negative 2 cubed over 3 minus negative 2 squared over 2. And then whatever the result of this expression equals, which I did not work out, would be the answer to that area in yellow. So you may go ahead and work that example out. You would have to work it out without a calculator. I kind of choose to leave that to you to do, so fill that answer in. Now again, they can make this example kind of more challenging. They can include sines, cosines, anything they want to. Now you're going to see that the heading of this one says a region lying between two intersecting graphs. but what happens when they intersect more than twice? Well, nothing happens. You just have to start thinking about how to set up that integral. Okay, so it says the sine and cosine curves intersect infinitely many times, bounding regions of equal areas. Now they say in a diagram, I'm not going to give you a diagram because you're going to be expected to find that on your own. Find the area of one of these regions. So my sine graph will do in orange. So y equals sine x will be presented in orange. So sine is middle, high, middle, low, middle, as we talked about in 30-1. And then that cycle will repeat itself. So imagine you pick up your pencil again, middle, high, middle, low, middle. There's another cycle. My cosine graph, I'm going to represent that in pink. Now cosine is different because it starts at 1, so high, middle, low, middle, high. So there's one cycle of cosine. Now what you're going to notice is that this is the little section that's being formed, and as these cycles continue, that section is going to be formed again. So this is the area that I'm interested in finding. Now you do need to know, where do sine and cosine intersect? Where is sine equal to cosine? Now from 30-1, if I divide both sides by cosine x, I'm going to get tan x is equal to 1. My reference angle, where does tan equal 1, is at pi over 4. Based on my cast rule, there's 2 quadrants where tan is going to be positive. So one of them is in quadrant 1. The other one is in quadrant 3, which I would do, my rotational angle is pi plus pi over 4, which would be 5 pi over 4. So those are my 2 intersecting points. That's important because the shading starts at the first one and the shading ends at the second one. So I'm going to set up my integral. It's going to go from pi over 4 to 5 pi over 4. And then which function sits on the top? So if I were to take a vertical slice in blue, you need to ask yourself, does the top function always stay the orange? And the answer is yes. So my top function is the orange function, which is sine x. My bottom function is the pink function, which is cos x, and then I'm integrating with respect to x. So let's go ahead and integrate that. The integral of sine x is negative cos x. The integral of cos x is sine x, but there's already that negative sign there. And I'm evaluating from pi over 4 to 5 pi over 4. And then you just be careful and sub in the values. So minus cos 5 pi over 4 minus sine of 5 pi over 4 minus negative cosine of pi over 4 minus sine pi over 4. So just carefully go through that. And when you do that, you're going to get cosine is negative in quadrant 3. So it'd be root 2 over 2. The negatives will cancel out. Sine is also negative in quadrant 3. So sine of 5 pi over 4 will be positive root 2 over 2 minus. Now cosine of pi over 4 is positive, but there's a negative out in front, so minus root 2 over 2. And then again, sine of pi over 4 in quadrant 1 is positive, but there's a negative sign, so negative root 2 over 2. So when you add that all up, the negatives will cancel to positives. You get 4 root 2 over 2's, which simplifies to 2 root 2 as my final area under the curve for one of those sections. And then that section gets repeated infinitely many times. Now, when we look at this example, there's here in the previous example, the graph intersected at 2 points, and then we have a section that's being repeated. In this next example, we have more than one intersection point happening. So you have to be really careful and you have to sketch this graph. So let's go ahead and think about this. Again, there's a graph tab here, but you can notice I didn't pull it out because I'd expect you to be able to do it. I'm going to factor out the x on the f of x graph. I get 3x squared minus x minus 10. And then I would continue to factor that. I need two numbers to multiply to negative 30, add to negative 1. I know that's going to be possible. So I'm going to go ahead and factor that, which if I do my work correctly, this should be 3x plus 5, x minus 2. So 3x squared minus 6 plus 5 is a minus 1. 5 times 2 is minus 10, which means this graph's x-intercepts are at 0, negative 5/3, and positive 2. And then when I look at g of x, and I factor out a negative x, my graph is x minus 2, so there's x-intercepts at 0 and 2. And so let's go ahead and sketch these graphs. We know that the end behavior on this graph is quadrant 3 to quadrant 1 for that. Because this has a negative coefficient, my end behavior is quadrant 3 to 4. Again, you're using your 30-1 knowledge to do that. I'm going to go ahead and draw the graph on this side here. So f of x is going to intersect at 0. Okay, so I'm going to do f of x in orange. It's going to intersect at negative 5/3, which I'm going to throw right there. And it's going to intersect at positive 2. I know it's going to do quadrant 3 to 1 behavior. So I'm just going to kind of throw in what I think it's going to look like and just sketch that in. And then I'm going to go ahead and draw my g of x graph, which is a parabola opening down. It has an intersection point at 0, and it also intersects at this point, which is 2. So I'm going to draw this parabola that opens down. I don't know where the vertex is going to be. I'm just going to draw it in like this. So now what's going to happen is you got to ask yourself, is it going to intersect more here? And the answer is yes. So we need to extend this graph a little bit more. And it intersects. So let's highlight the sections we're interested in. Now there's this section in yellow. Now I've probably exaggerated this graph, and then there's this section here that are the sections that lie between the two functions. So what we want to do is we want to take a vertical slice, and you want to ask yourself, is anywhere in the yellow does my function stay the same? In this little bubble, the pink function is always on top, but in this little section, the orange function is always on top. So we now have to break up our integral into two parts. We're going to have to break up our integral from the first intersecting point. Now, again, in this example, we've only found the x-intercepts. We didn't find the intersecting points between the graphs. So what I'm going to do is I'm going to go ahead and find the intersecting points by making the functions equal to one another. 3x cubed minus x squared minus 10x equals negative x squared plus 2x. I'm going to move everything to the left-hand side, so I get 3x cubed. The x squareds are going to cancel out. I'm going to get minus 12x equals 0. I'm going to factor out a 3x. I get x squared minus 4 equals 0. So the intersecting points are at 0, 2, and minus 2. So this first intersecting point is at negative 2. They intersect at 0 and they intersect at positive 2. So my first integral is going to be set up from minus 2 to 0. My top function is the orange, which will be 3x cubed minus x squared minus 10x. Minus my pink function is the bottom, which is minus x squared plus 2x. And we're integrating with respect to x. And then we add on that next little yellow section where the top and the bottom change. So from 0 to 2, this time my top function is the pink minus the bottom function, which is the orange. And then I'm integrating with respect to x. So when you go ahead and actually integrate all of this, you're going to simplify, integrate, do some work. Okay, you can also check using math number 9 function int. Just double check. You should get a final answer of 24 if my answer key was correct here. So you just work that out. If there's more intersection points, there may be more sections you have to break up your graph into. Now the last example, what we're going to do is we're going to kind of throw the function in reverse. So instead of doing going from left to right and doing top curve minus bottom curve, we're going to go from bottom to top. And it's almost like we're reversing the variables a bit. And then instead of doing top minus bottom, we're going to do the right minus left, but I would have to rewrite these functions in terms of y instead of x. Now you'll notice in a given question that you may have to do this because instead of the formulas being given as y equals a function of x, they're being given as x equals a function of y. So let's go ahead and graph it. So x is 3 minus y squared. Like normally, if I were to switch this around, we would find the x-intercepts, which would be at, so x-intercepts would be at plus or minus root 3. So this time my y-intercepts are at plus or minus root 3. So when I draw my graph this time, when y is plus 3, and I'm going to do this function in orange, when my y-intercept is root 3, let's say it's there, and negative root 3. Now I want to decide where is one other point on this graph. So if y equals 0, and I isolate for x is equal to 3. So I'm going to plot that one more point. When x is 3, y is 0. So that's right over here. So I know that my graph is going to open up right to left. So there's my parabola. So instead of it being up and down, it's being right and left. This coefficient is negative, which is kind of in the reverse, like negative direction. So left is sort of like that negative direction. And then I want to plot this function in pink, let's call it. And in this one, I'm just going to rearrange for y, which is So I'm going to leave the y on the right, leave the x on the left. So this will be x minus 1. And then I'm going to plot that function normally. So when x is 0, y is negative 1. When y is 0, x is positive 1. And I'm going to just go ahead and sketch that function, which is in pink. So now we're going to do the same thing. We're going to shade in the area of interest in yellow. But instead of taking vertical slices to check, I'm taking horizontal slices. So I'm going to take slices left to right. You want to ask yourself, does the right function always stay on the orange? And does the left function always stay on the pink? And the answer is yes. So when we set up our integral, we're going to go from where does the shading start, which will be that value. Where does the shading end, which will be that value. And these values are found by getting the intersecting points between the pink and the white. So I'm going to go 3 minus y squared, and this is for the other example, equals y plus 1. So instead of solving for x, I'm solving for the y points, which is important anyways. Y squared plus y, everything's moving to the right, equal minus 2 equals 0. So I'm going to factor y plus 2, y minus 1 equals 0. So y is equal to negative 2 and positive 1. That's super important because those are those values there. And I don't even need to find the x coordinates for those values because it doesn't matter. But if I needed to, you can sub them back into either the orange or the pink up there. So now when I set up my integral, it's going to go from bottom to top, right function, which is the orange one, minus the left function, which is the pink one. And instead of integrating with respect to x, we make sure everything is in terms of y, and we integrate with respect to y. So now I get 3 minus y squared minus y minus 1, integrating from minus 2 to 1 dy. Combine the 3 and the negative 1 to be 2, negative 2 to 1 2 minus y squared minus y dy. So the integral is 2y minus y cubed over 3 minus y squared over 2. I evaluate from minus 2 to 1. And then again, I'm just going to let you work that out. Work me out. And then that would represent your final answer. When you want to double check your answer, you just throw it in your calculator and work that out. Now, what I would recommend you guys doing is trying some of these examples below here. And if you run into any trouble, send me an email or log into Google Meet during our class time. Our practice booklets will have this in as well in it. This is going to be the primary content of I-4. So I'm going to ask you area under curves, and then areas between curves. And on your assessment, I'm going to make you do it with the left to right, top minus bottom idea. I will ask you both of these, dx, or you'll also be responsible for knowing the bottom to top, right minus left idea with respect to y. And then that's our lesson for today.